In the previous lecture we discussed the EX diagrams of a heterojunction under equilibrium, a PN junction under high forward bias, and two dimensional band diagrams. Then we also showed how the band diagram can be used as a tool for analysis of PN junction or deriving information about hole concentration, electron concentration, electron current density, hole current density, potential and electric fields, apart from representing a known distribution of electrons, holes, Jn, Jp, psi and E. In this lecture we shall discuss the correspondence between Ek and Ex diagrams, and then we shall summarize the important points of the entire module. Let us consider correspondence between Ex and Ek diagrams. Now we shall discuss the topic by representing the same process in both diagrams. The processes we shall consider would be recombination, three different types of recombination, namely direct, SRH and Auger. I will leave it as an assignment to the student to show on the Ex and Ek diagrams the corresponding generation processes, okay. And then we shall show how drift of electrons can be represented on Ex and Ek diagrams. Let us show the recombination phenomena. So this vertical axis is E and the horizontal axis is K. So this is the Ek diagram. Let us show the recombination phenomena assuming a uniform semiconductor. So this means that conduction band edge and valence band edge, these will be drawn as flat lines, okay. So this is as a function of x. So this is your Ek diagram and this is your Ex diagram. We are considering an indirect band gap semiconductor like silicon. Supposing I want to show a direct recombination, something like this. On the Ek diagram it would look like this. This means the electron undergoes a change in energy equal to energy gap, and at the same time it undergoes a change in momentum, crystal momentum, represented by delta k. So actual change in momentum, crystal momentum would be h cross delta k. Supposing I want to show SRH recombination. So the electron falls into a trap and then it falls into the valence band. Now how would that look? It would look something like this. So suppose this is the trap level at the same energy level here. So trap level to valence band edge is a vertical transition and this is a non-vertical transition. So in this transition it is undergoing a change in, electron is undergoing a change in energy as well as crystal momentum. Therefore particle emitted as a result of this process, so that is the particle which will take away the energy and momentum of the electron when the electron falls from here to here, would be a phonon. On the other hand, in this transition there is insignificant momentum change, there is only an energy change, and therefore the particle which will take away this energy would be a photon. Let us show one more process, that is the Auger recombination. So in this, an electron falls from the conduction to valence band directly, and its energy and momentum is taken away by, let us say, a free electron. You can also have a hole taking away the energy. You can draw the process on the EK diagram in the same way as I will do for the case when the energy of the recombining electron, energy and momentum of the recombining electron is taken away by the by an electron rather than a hole. So in order to avoid cluttering this diagram, I will draw the EK diagram on this side and show this process on that EK diagram. So this process is represented by this arrow, is energy and this is the wave vector, and this process is represented by an electron changing its state in the conduction band, say something like this. So this is the momentum change delta k for the recombining electron, and the energy change is Eg. Now it may not be possible to find a conduction electron whose energy and momentum relation is exactly given by this Eg versus delta k. That is, if I consider an electron which will take away the energy Eg, the momentum of that electron may not be exactly equal to delta k, because it all depends on the effective mass or curvature of this diagram. If I really want to know what will be the momentum of the electron, of this electron that has an energy Eg, I should take this energy interval and place it here and draw a line like this, and then I will get this point, and this difference would be the momentum of this conduction electron, okay, which is taking away the energy and momentum of this recombining electron. So this momentum change may not be exactly be equal to this momentum change, and therefore you really want to have conservation of energy and momentum, there should be another particle, some phonon, okay, for example, which may take away the remaining energy and momentum. However, this electron will take away most of the energy and momentum. Therefore, it has been shown using this particular transition where this energy is little less than the energy gap. So this is the kinetic energy of the electron which is taking away the energy and momentum of the recombining electron. This kinetic energy has been shown a little less than Eg because the momentum of this electron is not same as delta k, in fact it is less than delta k. Therefore, we should allow some third particle to take away the momentum, and therefore it will have its energy also. You can't have a particle which has only momentum and no energy, right? So therefore it can be a photon, it can be a phonon. Now even a photon is possible, in which case it will take away the energy but it will not have any momentum. So that would be a transition. I take this delta k and put this delta k here and take the energy corresponding to that delta k, I will get some energy. If that energy turns out to be less than Eg, then the remaining energy can be taken away by photon. However, if the curvature of the EK diagram is such that that energy is more than the Eg, then such a thing is not possible. In other words, in that particular case material, the Auger recombination cannot release a photon. So this is how you can decide what kind of particles will be involved in recombination from drawing the recombination process in both Ex and Ek diagram. So Ex diagram will only give you energy changes, whereas Ek diagram will give you both momentum and energy changes. Now let us show the drift process on Ex and Ek diagrams. So you have a semiconductor like this. Let us assume a uniform semiconductor to which a voltage has been applied, and you want to show the drift process here, okay. So semiconductor may be N type or P type, let us say it is N type. Now if you show the process only on EX diagram, it would look like this. So this side is positive, so your conduction band edge and valence band edge would be something like this. We have drawn this band diagram in one of the earlier lectures, right? Uniform semiconductor, a bias has been applied. This would be the so called quasi Fermi levels, EFN equal to EFP, because this is n type, this is close to EC. But right now this Fermi level is really not important for us. So if I want to show now the motion of an electron that is drifting from the negative contact to positive contact, so this is the direction of motion of electron. Now whatever I show for electron, you can show a similar thing for holes yourself. So the electron will be starting from, let us say here, it will travel some distance and then it will encounter a collision or scattering, so its momentum will get randomized, velocity will get randomized, it will again start and then scattered and so on. So this is the path of the electron on an EX diagram. So between two collisions its energy remains constant, okay, but its potential energy is decreasing, so potential energy is being converted into kinetic energy. So the difference between the energy of the electron and the conduction band edge indicates the kinetic energy. So its kinetic energy is going on increasing, its velocity is going on increasing, because the electron is accelerating in response to an electric field which is there in this sample in this direction. Okay, now how do you show this process on an EK diagram also? Now in this case I will have to draw an EK diagram for each position x, because the EK diagram will vary with x. So how do we do that? So let me repeat this diagram here. So this is your Ex, so this direction is x. Now let us assume that I use this axis to show the k vector, okay. Let us assume a simple EK relation, and this axis is anyway energy. So if I for example draw an EK diagram at say this point, it would look something like this. So this is your k, right. So this is your EK relation. So it is being drawn in this direction, so it is really perpendicular to the board. This is what you should imagine. So in the surface of the board is x direction, this k direction is perpendicular to the board, and so EK is drawn like this. Okay, now at another point if I want to draw EK, here it would be so similar EK diagram I should draw here. Okay, so this is the EK relation. Now an electron starts from here and it moves in this direction. So this part, when I want to show it on EK diagram also, then it is moving like this. At each point you can draw an EK diagram. So as it is gaining energy, it is gaining momentum as well. So you can see here that this difference is the momentum. This is the line corresponding to 0 momentum, right. This is k equal to 0. So this distance on this diagram represents the momentum that the electron has gained when it comes here at this x, and when it is getting scattered it is falling down. So on the EK diagram that transition can be shown something like this. Its momentum is getting randomized, it comes back to the top of the bottom of the conduction band, that is at EC, and then it starts again. So I can repeat this process. So I like to draw another EK diagram here to show the next. So this is how the electron moves on the EK diagram when EK diagram is varying with x. That is what is happening in the drift phenomenon. Okay, so it is very important to visualize processes in both Ex and Ek diagrams. That gives you a lot of insight. So in the case of recombination phenomena, for example, what kind of particles will be involved when electron recombines with a hole? What kind of mechanisms are possible depending on the material? Such things can be understood from the representation of the process on both Ex and Ek diagrams. Now let us begin a summary of the entire module. We started this module by answering the question, what is an energy band diagram? So we said energy band is a powerful concept which expresses physical conditions through a set of lines. So the set of lines were something like this. So the diagram has two parts, E versus x as well as E versus k. Here we have shown a one dimensional picture. Essentially E versus x means E versus space, okay, and similarly E versus k here in 3 dimensions it would mean E versus kx, ky and kz. So there is a correspondence between the Ek diagram and the Ex diagram. So if the energy levels are varying with x, then the Ek diagram shows you the energy momentum relation at any x. These two diagrams Ek and Ex are complementary, so together they represent in totality the information. So each part has only partial information. Why energy band diagram? So we said, and we in fact demonstrated, that Ex diagram helps us to represent or analyze. So it is both a representation tool and analysis tool. So it helps us represent and analyze the distributions of n, p, jn, jp, e and psi within a device. So in analogy to any graph, the energy band diagram is both a representation and a problem solving tool. So you know that any graph is both a representation and a problem solving tool. For example, let us take this equation. I can use graph as a representation tool. To represent this equation, it would be something like this. So this is y and this is x. Let me give an example where graph is used as a problem solving tool. Supposing I have two equations, y equal to m1x plus c1 and y equal to m2x plus c2, and I want to solve these two equations simultaneously, that is get the values of y and x which satisfy both equations. Now you can do it solely by algebraic manipulation, or you can do graphically. So what do? I represent this line on the graph, which is this one, and I represent this line also on the graph. So maybe it is something like this, and then the point of intersection is actually the solution of these two equations, okay. So this x naught y naught is the solution. So this is how you have used graph as a problem solving tool, okay. So energy band diagram is also a graph. It can be used both as a representation tool or problem solving tool. The Ek diagram yields the group velocity, the crystal momentum and effective mass of a carrier for a given energy, and thus helps us analyze the interactions of a carrier with other entities in the crystal. Electron motion in a region of varying potential. So we said, by considering different variations of the potential, the following: if the potential varies slowly over a length scale of de Broglie wavelength of the electron, thermal average de Broglie wavelength, lambda thermal. So this is a slow variation. Then the motion of the electron is governed by Newton's second law. On the other hand, if it varies rapidly over the same length scale, so you can see the length over which the variation is occurring here is smaller than lambda thermal. So another example of that is the crystal potential, where there are rapid periodic variations in the potential. If you see the length scale A, it is much less than lambda thermal. A is the distance between two consecutive atoms. Then in both these cases, the motion is governed by Schrödinger's equation, and that is why to analyze the motion of an electron in a crystal, we must start from the Schrödinger's equation. Then we discussed energy band formation. So first we gave a qualitative model which reasoned as follows: electrons in an isolated atom are in a potential well. So this is a potential well corresponding to a single atom, and then you can put together many atoms, in which case your potential variation will look something like this. So same potential variation when you superpose for a large number of atoms placed very close to each other would look something like this. So for an isolated atom the energy levels would be discrete, something like this, whereas for electrons in a crystal each level spreads into a band of energies, band of allowed energies separated by band of energies which are not allowed, so forbidden energies. This splitting of an energy level or spreading of an energy level into a band can be visualized as consequence of Pauli's exclusion principle, in which, or according to which, no two electrons in a system can have the same energy. So when you put a large number of atoms together, all their electrons cannot have the same energy which they had when the atoms were isolated. So therefore they have developed different energies, and since there are so many electrons, their energies are very close to each other, and so the allowed energies becomes a band. This approach of developing the allowed energy bands from discrete levels of isolated atoms is referred to as the Bloch tight binding or linear combination of atomic orbitals approach. You can have an alternate approach in which you develop the development of forbidden energy bands rather than allowed energy bands from the picture of free electrons, in which all the energies are allowed for the free electrons. So from a continuous band of allowed energies you are developing forbidden bands. This approach is referred to as Brillouin nearly free electron or single electron approach. Then we considered a quantitative model of energy band formation. To simplify calculations and analysis, we approximated the actual potential picture. Okay? So for an isolated atom we assumed that the potential well is rectangular of width L, and then we showed that if you solve the energies for the electrons from Schrödinger's equation, you get this kind of an EK relation. So the equations used were as follows. So this is the Schrödinger's equation, which depends only on the space. We have removed the time dependent part because this is how we solve the Schrödinger's equation, where this K is related to the electronic energy. The solution of this equation is, as shown here, consists of a combination of two complex exponentials, and if you impose the boundary conditions corresponding to the rectangular well, so this is actually a Schrödinger's equation written for a constant potential region, right, and that constant potential has been assumed to be 0, and the fact that at the boundaries x equal to 0 and x is equal to L, the potential energy goes to infinity. In here it is shown to be going to E naught. In practice this E naught, this vertical height is very large, so we can assume it to be approximately infinity, in which case the wave function goes to 0 at both x equal to 0 and x is equal to L. So that is why we assumed the boundary condition to be wave function going to approximately 0, assuming an infinite potential well. Putting these boundary conditions on this equation, the solution is a sinusoid or cosine function, and the K here therefore becomes discretized according to this formula. where n is equal to plus or minus 1, 2 and so on. Now the same information has been represented graphically here. So these are the different values of k, and if you put these values of k in this formula, you get this relation between E and other parameters of this situation. So these are the energies. So discretization of energy is a consequence of discretization of k, which is a consequence of the boundary condition that wave function goes to 0 at both these ends. We adopted a similar approach for a periodic potential, and in this case we showed that the EK relation is considerably more complex than what we showed here. The differences being, instead of allowed energies, discrete energies, you have allowed bands. Secondly, the EK relation is periodic. Here it is a point. Here EK relation is periodic with a period equal to 2 pi by a. And third, for every value of k you have many values of energy. So the EK relation is a multi-valued function of k, whereas here for any given value of k you have only one energy. Now these kind of features were a consequence of the Schrodinger's equation for this particular situation. So Schrodinger's equation is written in this form, where UC is the crystal potential. Again, for quantitative modeling we assume a rectangular kind of shape for the periodic potential, okay, so that the analysis becomes simple. So UCX is periodic with a period equal to a, which is the interatomic distance. So we consider a one dimensional crystal where all atoms are arranged in one dimension only. According to Bloch's theorem, for this kind of a Schrodinger's equation, the solution psi x is of the form ukx into e power jkx. So the e power jkx type of solution for constant potential gets modulated by a Bloch function ukx, where this function has the same periodicity as the crystal potential. Now consequence of this kind of situation is that the EK relation is even, so E of k is equal to E of minus k. We argued why this should be so, and further E of k is periodic with period 2 pi by a. So both these are consequences of this kind of a solution of the Schrodinger's equation for periodic crystal potential. We gave an example of a wave function for a periodic crystal potential, how it looks. So in this example UCX was shown something like this, and the Bloch wave had this kind of a shape. This is just to give you a feel for how the wave function looks like for periodic crystal potential. And this is the exponential, the complex exponential. We can take either real or imaginary part, and the wave function is obtained by multiplying this e power jkx with the modulating function uk of x. Okay, so this is a function. When you multiply these two, you get a function like this. So you see the wave function of an electron in a periodic crystal potential is fairly complex. Then we discussed features of the EK diagram. This form of representation of the EK diagram is referred to as periodic zone representation. So you see that the EK relation is being shown for several periods, even though it is periodic, and you can probably show the information only in one of the periods, and then the same thing will apply to other periods. That is why you come up with a reduced zone representation where you can show just one period from minus pi by a to plus pi by a. Further, if here also the function is even, you can even restrict the information to just 0 to pi by a, because the same thing will be reflected on the region 0 to minus pi by a. So in fact this is the kind of thing that is used to show EK diagrams of real semiconductors, which are more complex. For example, here for silicon in the 100 direction, the EK diagram looks something like this. The bottom of the conduction band and top of the valence band are not at the same value of k. in contrast to the situation in the Kronig-Penney model or the simple one dimensional case with rectangular potentials. You can use the other half to represent the EK relation in another direction. So this way you can make a compact representation of a lot of information on the same graph. So in fact that is what is done. So another principal axis, crystal axis, is 1 1 1. So the EK diagram in that direction is shown on this side. Evidently this is different from this. So for example, you can see that the difference between the bottom of the conduction band and top of the valence band, which is the energy gap on 111 side, is more than that on the 100 side. So you will find the EK diagram for silicon to be shown mostly on the 100 side, or you will find in analysis this particular part of the diagram being shown often, because it is the smallest energy gap that is of interest. For gallium arsenide, the EK diagram is different from silicon in that the bottom of the conduction band is right above the top of the valence band. So this is a direct band gap semiconductor, whereas here an electron jumping from conduction to valence band will undergo a change in energy as well as momentum, and therefore more likely transition is that electron jumps into an intermediate level first and then jumps into the valence band. So it makes an indirect transition, okay, that is more likely, therefore this is called an indirect band gap semiconductor. Here however the electron in the conduction band can jump directly into the valence band, okay. The utility of the EK relation, we pointed out that the EK relation can be used to get crystal momentum, because the force on the electron in a crystal is equal to the time derivative of the product H cross k. So this implies Hk is conserved in the interaction of electrons with a force or other entities, and that is the reason why it is called a momentum, namely the crystal momentum. However, it is not the true instantaneous momentum, since the true instantaneous momentum is mass of the electron multiplied by velocity of the electron, but we have shown that H cross k is not of this form, therefore it should not be regarded as true instantaneous momentum. You can use the EK relation to derive quantities, such as if I differentiate the EK relation, then I can get the group velocity. So this is a typical EK relation and it gives you a group velocity something like this. We showed what is the meaning of this kind of a variation of the group velocity. If you double differentiate the EK relation and take a reciprocal, you get the effective mass. So for this EK relation, your effective mass picture is something as shown here. So if I restrict myself to a small region around this point, okay, here, then this EK relation will be approximately a parabola, and therefore its double derivative will be constant, and that is the origin of the use of a constant effective mass in many cases, so long as the energy of the electron does not become very high. Kinetic energy of the electron does not become very high. So for this point the kinetic energy is 0, and its kinetic energy, as it increases, it moves up. The electron moves up on this EK diagram. Now the effective mass is actually a tensor, because in a crystal the acceleration experienced by the electron is not in the same line as the force. So the acceleration and force are non-collinear. So therefore you have this kind of relation between acceleration and force, and you get a matrix representation of the effective mass. You can determine each element of the matrix using a formula like this. So if I want Mij, where I and j can be x, y or z. So Mij, reciprocal of this, is equal to the acceleration by the force. The acceleration is in the I direction, and this acceleration in I direction is in response to a force in the j direction. Then you can write this as d by dt of Vgi by d by dt of h cross k in the j direction, because acceleration is time derivative of the group velocity and force is time derivative of the crystal momentum, and then simplifying this formula results in a formula like this: dou square E by dou of h cross k I into dou of h cross k j, that is the effective mass, reciprocal of the effective mass Mij. Now very often we assume that the Ek relation is parabolic, is a paraboloid in 3 dimensions, right? It is parabolic in 1 dimension, and in such a case what happens is you have only the diagonal terms of the effective mass matrix mxx, myy and mzz. Other terms become 0. This can be easily seen by applying this formula for this kind of a situation. So apply this formula for this parabolic relation and you will end up getting this fact. In real semiconductors, how are effective masses determined? Real semiconductors are 3 dimensional, so you have kx, ky and kz, all 3 dimensions to be considered. For the case of silicon, the 100 direction is very important because the energy gap corresponds to the energy gap of the Ek relation in this direction. Let us assume that kx is 100, okay, and if you represent the Ek relation of the electron in the conduction band as a paraboloid, assuming the bottom of the conduction band to be origin here, okay. So this point is origin, so therefore the left hand side becomes simple, it is simply E. The effective mass term coming here is referred to as longitudinal because it is in the direction of the principal axis 100, okay, kx. Ky and kz are transfers to this axis, therefore the effective mass terms coming here are represented by the symbol mt. So this is transverse, so transfers to this where kx is assumed to be the principal 100 direction. Now we have put the same mt for both these terms ky and kz terms because it turns out that the shape of the paraboloid for silicon is such that the curvature in ky and kz directions are identical. It turns out that ml is 0.98 times the mass of electron in vacuum and mt is 0.19 times mass of electron in vacuum, and from this ml and mt you can determine effective masses for different situations. 2 situations are conductivity and density of states. So the conductivity effective mass is obtained by averaging the conductivity in x, y and z directions, and the result of this is an equation Mn equal to 3 times 1 by ml plus 2 by mt reciprocal. So this is a kind of a harmonic mean of ml, mt and ml and mt in the 2 other directions, that is why the factor 2. So this value turns out to be 0.26 m naught if you substitute these values of ml and mt. Using the same values of ml and mt, in the case of density of states however, the effective mass is different, 1.08 times m naught, because a detailed derivation shows that the averaging is of a geometric kind. There is a geometric mean ml into mt square whole thing raised to 1 by 3 with of course a factor coming here. For the case of gallium arsenide, similar approach yields you a same conductivity and density of states effective mass. The reason in this case ml and mt are both identical and equal to 0.067 m naught. So you see, if you compare it with silicon, the effective mass of electron in gallium arsenide is much smaller, right. So electron feels much lighter in presence of gallium arsenide crystal potential as compared to silicon crystal potential, and that is why the mobility of electrons in gallium arsenide is very high. So you apply force, because the mass is small, the electron gains a high acceleration or high drift velocity as compared to in gallium arsenide as compared to silicon. Various energy levels in the Ex diagram. From Ek diagram we moved on to Ex diagram. So the energy levels can be shown to emerge from the Ek diagram. The 2 energy levels which emerge from the Ek diagram are Ec and Ev, bottom of the conduction band and top of the valence band. A variation of Ec and Ev as a function of x enables you to get the picture of the Ek relation throughout the volume of the device. So Ec and Evex as a function of x reflect the spatial variation of the Ek relation. You get the level E naught from the crystal potential, which is responsible for the conduction and valence bands. Okay. So E naught versus x reflects the spatial variation of electrostatic potential psi or electrostatic field E of the drift diffusion model. So this because the energy E naught corresponds to the energy of an electron touching the semiconductor from outside or from vacuum, and you can easily show that as you move this electron over the surface, it will experience psi or E of the semiconductor. Now E naught serves as a reference while comparing electron energies in different isolated materials. So E naught really is very important. In practice, we do not show the conduction and valence bands and crystal potentials because the energy band diagram, that is the Ex diagram, will become very complex. We just extract the levels E naught, Ec and Ev and show their variation with respect to x. So the E naught variation is obtained from the drift diffusion model formula. Okay. So here the relation between E naught and psi is E naught by q equal to constant minus psi, or gradient of E naught by q is E. You can locate Ec below E naught by a value q chi, where this electron affinity is obtained from the Ek diagram and crystal potential. So chi can be a function of x if the crystal potential is varying with x, as it happens in a heterostructure or compositionally graded structure. Similarly, Eg as a function of x can be also obtained from Ek diagram and doping profile. We have shown that the energy gap is a function of doping, and for heavy doping the energy gap decreases. So if the doping varies in a semiconductor as a function of x, for example, the energy gap can change as a function of x. Energy gap can also change if the composition is varying as a function of x. So from this energy gap you can locate the Ev below Ec. You can locate the quasi-Fermi level for electrons below Ec using this formula. Okay. Another relation that is related to variation of the quasi-Fermi level is this equation of the drift diffusion model, wherein the electron current density is represented in a compact form in terms of the gradient of the quasi-Fermi level. So both drift and diffusion are compressed in this one term. One can similarly locate EFP from Ev using this formulae. You also have a formula for gradient of EFP in analogy to the formula for gradient of EFN. So EFN and EFP as a function of x reflect the distributions of NP or JNJP of the drift diffusion model. So these two formulae show the relation of EFN and EFP with concentrations, whereas these two formulae for gradient of EFN and gradient of EFP show the relation between the variation of EFN and EFP with current densities Jn and Jp. You can also locate the quasi-Fermi level for electrons and holes with reference to Ei using these formulae. You can locate within the energy gap the energy levels corresponding to impurities or defects. So Ed, Et and Ea as a function of x reflect the defect or impurity distributions. We outlined a procedure for constructing an Ex diagram. This procedure is very important. If you follow this procedure properly, then you can draw an Ex diagram for even a very complex situation where composition, doping and so on are changing with distance in a device and a voltage has been applied in a very easy manner. So the first step is to solve for n or jn, p or jp and psi or E versus x from the drift diffusion model. So this is the first step. So here we are looking at Ex diagram as a representation tool for conditions in the semiconductor. So these are the drift diffusion model equations from which you get this information. In the next step you draw the device physically and locate the junction, space charge and neutral regions. An important point, the direction of the charge transfer during the junction formation can give an idea of the relative widths of the space charge region on either side of the junction. So when you are drawing the energy band diagram, E as a function of x, you would like to know what is the width of the space charge region on either side of the junction, at least the relative values or relative qualitatively the relative magnitudes. So this information is obtained from the direction of charge transfer. And how does the charge transfer occur? Electrons are transferred from high EF region to low EF region. So you draw the band diagram with the two materials separated and see the relative values of EF. After that, you can build up the band diagram in the following order. So first draw continuous EFN and EFP everywhere from a knowledge of applied voltage and current densities. In this, first draw the quasi-Fermi levels in the neutral region and first draw the majority carrier quasi-Fermi levels, okay, and then the minority carrier quasi-Fermi levels. The reason why you start from EFN and EFP is because EFN and EFP are either constant or monotonic for all x. We have given reason for this. Reason why EFN and EFP is continuous is because any abrupt change in EFN or EFP would mean infinite currents which are not possible physically. Second important reason for using EFN and EFP is that EFN and EFP are directly related, the variation of EFN and EFP are directly related to the applied voltage when the device contacts are ohmic. So if you have ohmic contacts at x equal to 0 and L, then EFN 0 minus EFN L is Q times V. EFP 0 minus EFP L is also Q times V. So the total variation of the quasi-Fermi levels in the device would be equal to the applied voltage provided the contacts are ohmic. It does not matter what kind of a complicated material structure this region has. The next step would be to draw EC and EV in neutral regions from a knowledge of energy gap, EFN, EFP, N and P. Then sketch E0 as a continuous line everywhere from a knowledge of electrostatic potential and chi. So note that we have assumed that we have used the drift diffusion model to solve for NP and psi before we start drawing the band diagram. Now why should E0 be continuous? Because any abrupt change in E0 means an infinite electric field at that point, which is non-physical. Next step would be to sketch EC and EV in insulator and space charge regions based on electron affinity and energy gap. Finally, one can sketch other levels like EI, ED, EA, ET if required. We explained various varieties of heterojunctions, type 1, type 2 and type 3, okay, depending on how the conduction and valence band edges are located for the wider band gap material with reference to the lower band gap material, okay. Now each of the above varieties or types can be either isotype or anisotype. Isotype means both sides are p or n type. Anisotype means one side polarity is opposite to the other side polarity. Finally, we discuss the correspondence between Ex and Ek diagrams. We did so by representing the same process in both diagrams, namely direct recombination, SRH recombination and Auger recombination and drift of electrons. So these are the diagrams, right. So direct recombination, SRH recombination, Auger recombination shown on this. So here this is direct and this is SRH, right, and here this process is Auger. Similarly, this is the method of representing drift on Ek diagram. Let us recapitulate in a minute the various learning outcomes. So we hope that after going through all this discussion, you are able to explain how the wave nature of electrons restricts the allowed energy E of electrons subjected to a periodic potential to certain energy bands. You are able to outline the features, methods of determination and utilities of Ek and Ex diagrams of a semiconductor So you are also able to point out the correspondence between these two diagrams. Explain the concept of crystal momentum. Determine the effective mass, group velocity and crystal momentum of an electron having an energy E from the EK diagram. Sketch and explain the EK diagrams of silicon and gallium arsenide. You should be able to determine and sketch the EX diagram of a uniform semiconductor under the following conditions: equilibrium for any doping and temperature, uniform volume generation and applied bias. You should be able to determine and sketch the EX diagram of a spatially non-uniform semiconductor under equilibrium, in which the doping and composition change abruptly at a point and gradually. You should be able to sketch and explain the EX diagram of a P plus N junction under high forward bias. Explain how the energy band diagram can be used to derive the exponential increase in the diode current with forward bias. And finally, sketch the one-dimensional band diagram and interpret a two-dimensional band diagram of any device. With that, we have come to the end of this module. We will start a fresh module in the next lecture.